You're listening to the Future Tech Health Podcast with Richard Jacobs. Until I reached age 40, I never realized the obvious, that we all have medical issues, or we at least have a family member or close relation that has, or will have them in the future. Medicine and biological systems are the final frontier. Until we've conquered death, figured out how life began, cured cancer, and understood our purpose in the universe, there's a heck of a lot to talk about when it comes to our health. Future Tech Health means I'll be covering futuristic topics that are actually already in clinical trials, or even starting to appear on shelves or by prescription, or available for your own use. We dive deep into stem cells, CRISPR-Cas9, the science of sleep, epigenetics, medical testing, cancer, ketogenic diets, stem cells, aging, regenerative medicine, and more. My goal for you, the listener, is to learn from these podcasts. You may very well learn something that may change the course of your life for the better, steer you towards a new career, or give you insight into addressing a serious medical problem. Remember, however, this podcast and its content is informational in nature only. No medical, tax, legal, financial, or psychological advice is being given. If you enjoy the podcast, please listen, subscribe, like, and share it with friends. Thank you. Hello, this is Richard Jacobs with the Future Tech Podcast. I have Alexey Potapov. He works with SingularityNet as an AI researcher, and we're going to be talking about their experiments with generative capsule networks. So I know about a little bit about generative adversarial networks, but not about generative capsule networks. So, Alexey, welcome. How are you doing?
Hello, Richard. I'm fine. And you?
Good. So what are generative capsule networks? What does that mean?
Actually, this was a short experiment 2 years ago, so maybe it's not the very best topic to discuss. But in any case, one of our main goals was to investigate the limitations of deep learning networks, and we studied different ways how to extend their capabilities, and we encountered a paper on capsule networks by Hinton and his colleagues. Basically, these capsule networks, they, to put in words, it's much more easier to draw on a board. So imagine you have a handwritten digit, like in a MNIST data set, and you have a network which you try to train to recognize different digits. And if you have the same digit rotated to different angles, traditional architectures, traditional models of formal neurons, they will need to actually learn to recognize this digit in all possible rotations. So they will do it not very efficiently, and they will not be able to extrapolate to different rotation angles, just to interpolate between them. And in general, you will not have a neuron except very high-level neurons, which will correspond to this digit and its parts. So, for example, if we have 6 or 9, it has they have a circle, they have some specific strokes, and these neural networks, traditional neural networks, they will fail to decompose these images of digits into the components.
Quick question here.
Yeah, okay.
Would you need a separate neural network for each digit? Or could you have one that would identify all 10 of them?
No, you don't really need a separate network to every digit, because you can train a network a larger, only one but larger network to incorporate all different digits in all different forms, and this network will somehow manage to learn shared representation, some shared information between different digits. So it's not that bad. You will be able to use one network to recognize them all. But what I mean is that for every rotation angle, it will learn a sort of its own decomposition. It's say convolutional neural network, and each convolutional map will correspond to a very specific stroke. So it will correspond to the same stroke in only one orientation, and another feature map will correspond maybe to the same stroke in another orientation. So it will fail to capture these regularities, to incorporate them into its representation of these images. And capsule networks, CapsNets, they are trying to overcome this limitation. They don't just pass activation levels, they also try to figure out transformations of these paths, receptive fields of each neural network, of each neuron, or convolution map will be augmented with these parameters of the transformation. And the hope was for these CapsNets that they will really learn how to represent a specific object and its subparts. It actually doesn't work that well, but it has some sense behind the idea.
Well, okay, one second. If the CapsNets are old, what is the latest and greatest, in this area? What are the new AIs called, and how do they work?
Well, CapsNets are not that old, and they still have some potential to be discovered because there are some quite novel works with the use of CapsNets. And but here, CapsNets were very popular 2 years ago, and people, some utility of them was found, but maybe they are missing something. So our idea was to create a generative capsule networks, because the basic model of CapsNets is discriminative. So they take images as input and produce their representations or results of recognition and so on. And in our experiments, we found out that generative models, they also have same limitations. So it's very difficult for them to learn invariants and to extrapolate beyond the domain of the training set. But yeah, okay. Our experiments were also of limited success, so we gained some improvements, but not as large as we hoped. Actually, if you ask me about the modern models, you may know that in natural language processing, such models as BERT, GDP, and so on, they are quite popular right now, and they are based on attention mechanisms, especially self-attention. And in fact, both CapsNets and self-attention based models, they share some common properties. So they go beyond traditional neural networks by introducing a sort of addressing. So it's a way how neurons can pass not only values but addresses.
What does that mean, addresses? What's an example of that?
Well, if we are talking about just programming languages, you can have a variable, and you can use this variable as a reference to the value which is stored in some memory cell. And this is what neural networks are not very well suited for. And actually, there was a seminal paper by Fodor and Palishin, which, it was something like 1986 or 8, I don't remember exactly. They criticized connectionist models like neural networks for their inability to solve the variable binding problem. So your neuron has a very fixed position, and it reacts on a very fixed stimuli. And if we consider symbolic systems, it's much more easier with symbolic systems. Actually, they can process such things naturally. You can just denote something by something and use this variable for in different places, and you will refer to the same thing in different places with the use of this variable, and you can bind a value to this variable. This is what is called a variable binding problem, and it leads to a very compositional stuff, which is very important for reasoning and so on. And this is what neural networks are lacking, and different models, both self-attention models, which give us a lot of cool modern stuff in natural language processing and computer vision also, and such models as CAPS-nets and other exotic models like HyperNets, which we also studied some time ago. They actually try to overcome this problem with variable binding. Again, if
what are some of the modern problems that you're looking to tackle? What just determining, this handwritten letter is the number 9 seems elementary. Like, what are the problems right now that you're looking to solve?
Well, if we go beyond basic models like CAPS-nets and so on, I mean basic in terms that they are building blocks of larger models, then we can go to some difficult problems which require this sort of stuff. For example, visual question answering is such a kind of problem. So you have an image, and you can ask nearly arbitrary questions about this image, like what is left to the tall building near a bus stop or something like this. And questions can have a really compositional nature. So you compose different components together, and it's very difficult for neural networks to process such compositional queries to our system. And here you also will face with problems like how to address different things, for example, for visual reasoning. And the visual question answering is, it of course has practical applications, but there are very practical tasks, which also require a sort of visual answering. For example, in the context of smart cities, we have such tasks as anomaly detection in road scenes, and you really should reason about images because there are different objects like pedestrians, cars, bicycles, traffic signs, and so on, and they interact with each other. And you should find compositional patterns of the interaction, and you should be able to reason about this. And if we are trying to build end-to-end deep neural network, it might be difficult to do this. That's actually why we switched from pure deep neural networks to neural symbolic systems, which are becoming quite popular right now. Okay.
Do you have to string together multiple AI systems or multiple neural network systems in order to solve problems, or is the attempt to have one network solve a larger problem? You know what I mean? Or do you have to pass along a problem or pass it back and forth between different neural networks in order to solve it?
End-to-end systems are very popular because it's very nice to be able to just take a neural network, a single neural network, which can be composed of different modules, but in any case, it's a single neural network which is trained with the use of one same loss function. It is trained from end to end, and it's really great if we can do this. But in practice, such systems can be trained for a very particular domain or very particular data set, and they will work not very well outside this particular data set. That's why, we consider hybrid systems, which can include different components, which can be pre-trained using different data sets, different tasks, and these components can be united by some other system. It's what we are doing with the use of cognitive architecture. So if we have a hybrid cognitive architecture, it can have different neural networks as subcomponents. For example, for the vision system, it will be one neural network. For audio system, it will be another network, and so on. So if we consider benchmarks, public benchmarks, which do have a very specific data set, then most likely state-of-the-art models which win these benchmarks, which show the best results on them, they will be a holistic one network which is trained end by end, and it can contain different components. For example, a convolutional neural network for image processing, and a recurrent neural network for the text input, if we are talking about visual question answering. But this neural network will specialize a lot. It will learn biases in this data set, and what is good for such benchmarks may be not very good for practical applications, and that's why in practice we really use hybrid systems with multiple components, including different neural networks in particular.
So what are some of the big problems that you're working on? What are some of the really tough ones that people want to solve right now with AI?
There are a lot of them actually, and it also really depends on what methods do you want to use. For example, in SingularityNet, some people are working on bioinformatics problems like revealing genes and their combinations which are associated with longevity. And they, for these purposes, they use symbolic pattern mining. And it's quite a general but not too popular tool. And it's really an important problem. So, there are very huge problems which cannot be solved right now. Like, let's try to solve the longevity problem on a biologic system level, and in this case, we will need a real AGI which can read papers, scientific papers on this stuff and so on. But if we are not talking about such large problems which cannot be solved right now, there are still many more local problems in different areas. Other my colleagues, for example, also in SingularityNet, are working on speech processing, and one of the problems is what to do if we have too few examples and these examples are too short. And we need to improve our deep neural network models or whatever. I'm not sure what problems to indicate. Another problem is personal assistance. There are many existing personal assistant applications like Siri. I don't remember all of them. We have Alice in Russia.
What is Alexa, Siri, etc.?
Alexa, Alice, Siri, and so on. They are not bad, but you can easily fool them, or maybe not fool, but they will not solve your tasks when you ask them something which requires reasoning. Actually, my personal experience with this type of software is that if I consider them as just a voice interface to a non-intelligent piece of software, I become much more comfortable with them because, in fact, they are really stupid. So it's just a sort of interface to the existing skills, and if I know which skills they have, this is like a menu. I can just select one thing from menu or another, and they cannot really reason, and I cannot ask them anything I want. And there are many possible ways to improve them using neural symbolic systems once again, because symbolic component allows them to reason. It's similar actually to the visual answer, to visual question answering, but instead of images, we can have here a history of our interactions with a personal assistant. So we can have a compositional type of question, like, please remember that I like this kind of pizza, and my friend don't like this kind of pizza, and please help us to find a restaurant which corresponds to both our preferences. So please select a restaurant with this kind of pizza, but without that kind of pizza. And no personal assistant right now can handle such a request. And it really requires a sort of compositional reasoning. Okay. So there are many tasks of different scale to be solved, still to be solved by artificial intelligence.
So my last question is, what do you think will happen in the next 5 or maybe even 10 years? What do you think AI will be able to accomplish?
Well, it's difficult to answer because in 10 years, even technological singularity may take place. On the one hand, on another hand, even self-driving cars can still be not reliable enough for total use. So we may hope that self-driving cars will be dominant, and humans will not drive anymore, and we will have much less car accidents, but I cannot promise that because this problem cannot be much more difficult than we've seen. So there is a very wide range of possibilities, from no total use of self-driving cars and up to technological singularity. But we can guess some stuff like we will have more and more robots in call centers everywhere and so on. But it's very difficult to guess what will surely happen in this time range and what will surely not happen.
Well, very good. Well, Alexey, thank you for coming on the call. I appreciate it very much.
Thank you, Richard. Bye. Bye.
Okay. Bye.
You're listening to the Future Tech Health Podcast with Richard Jacobs. Until I reached age 40, I never realized the obvious, that we all have medical issues, or we at least have a family member or close relation that has, or will have them in the future. Medicine and biological systems are the final frontier. Until we've conquered death, figured out how life began, cured cancer, and understood our purpose in the universe, there's a heck of a lot to talk about when it comes to our health. Future Tech Health means I'll be covering futuristic topics that are actually already in clinical trials, or even starting to appear on shelves or by prescription, or available for your own use. We dive deep into stem cells, CRISPR-Cas9, the science of sleep, epigenetics, medical testing, cancer, ketogenic diets, stem cells, aging, regenerative medicine, and more. My goal for you, the listener, is to learn from these podcasts. You may very well learn something that may change the course of your life for the better, steer you towards a new career, or give you insight into addressing a serious medical problem. Remember, however, this podcast and its content is informational in nature only. No medical, tax, legal, financial, or psychological advice is being given. If you enjoyed the podcast, please listen, subscribe, like, and share it with friends. Thank you.